Hello, hello, hello. Welcome everyone to the fourth of this year's Burlington House Lunchtime Scientist Talks. My name is Joe. Hopefully you've seen me before, but if this is your first time, hi. I work at the Linnean Society, which aims to inform, inspire, and involve people about nature and its significance through our special collections, our programs, and our scientific publications.
Hello, hi, my name is Lucinda, and I work at the Royal Astronomical Society, which encourages the study of astronomy, solar system science, geophysics, and other closely related branches of science.
It's great that our two organizations can be working together. We both live in Burlington House, which is this great big building in the center of London, alongside some other cultural organizations, including the Royal Academy of Arts, the Royal Society of Chemistry, the Geological Society, and the Society of Antiquaries. The Linnean Society and the RAS, the Royal Astronomical Society, have co-produced this series of great talks with great people for young people with an interest in astrobiology, what that means, to learn about the really exciting field and the variety of careers that people can have within it.
Before we get to our wonderful speaker today, I'm going to do a little bit of housekeeping. So just to let you know, this webinar is taking place on Zoom, and it is also streaming on YouTube. So we're streaming it both on the Royal Astronomical Society and Linnean Society YouTube channels today. And if you're watching this live, you can type questions or comments in the Q&A boxes, and our speaker will try to answer them at the end. On to our guest speaker today, who is Silvio Sinibaldi. He is a planetary protection expert at Airbus Defence and Space in the Stevenage, which is in between Cambridge and London. Silvio is currently working as a planetary protection and cleanliness and contamination officer on the ExoMars rover project, and he is part of international working groups on planetary protection and with the Airbus board to review European space specifications at industry level. With 15 years experience in industry, working in both civil and military aircraft and space sectors, I'm really excited to hear what Silvio has to say. Thank you for joining us today, Silvio. I'm going to hand it over to you now.
Thank you. Thank you, Lucinda, and thanks for the nice introduction. Thanks for having me today. With this presentation, I would like to introduce you to my discipline, what is planetary protection, its role within the astrobiology community, and how it's implemented at industry level in the astrobiology missions I'm working on. As you said, I work as planetary protection officer at Airbus Defence and Space in the UK. Just before diving into planetary protection, I thought, given the target audience, it was helpful to talk a little bit about me, my background, and my study and career path. So I was born in central Italy, in a region called Umbria, in a beautiful medieval village in the middle of nowhere. And when I was a teenager, what I wanted to do was playing football. Yeah, I wanted to become a footballer. And later on, when I was studying my GCSE, even later, A Level, I wanted to become a vet. Maybe because I was surrounded by nature and the farm and animals, but as you can see, I didn't have a very clear vision of what my future would have become. And for some reason, I ended studying material science at the University of Perugia in Italy, where I got a Bachelor of Science degree in 2005. Just before getting that degree, I decided to go for the Erasmus program. For those who don't know, this is an amazing initiative driven by the European Union, which allows students to go abroad while studying at university. And I went to southern Spain in the coast, in a city called Alicante. And because of Alicante wasn't a too bad place really to live and study, I stayed there a little bit more, and I got my Master of Science degree in nanomaterial and nanotechnology in general. It was 2007 when I then moved back to my home country, and I started my industry career in the aerospace field, working in a worldwide company and dealing with material and processes for civil and military aircraft. till 2013, which I must admit was a very important year for both my personal life and my career, because it's when I moved from Italy to the UK to follow my current British partner. And I started working for Airbus Defence and Space and being introduced to the space industry and to amazing astrobiology projects like ExoMars rover and Mars Sample Return, which I would like to talk to you in my next slide. February this year, I've been given a good opportunity from a very inspiring and competent group, this Astrobiology Open University, to study in planetary protection, which I would like also to spend a few words a little bit later on. So as you can see, as a summary, my takeaway from my study and career path is that if you are a GCSE student or even an A Level student and you don't have a clear view of what you want to become next, just don't worry too much. Because I'm a living example of somebody who didn't really have an understanding of what I wanted to be next. I started studying in a field and then ending, working in a apparently different one. My takeaway is that just take your time. It will become more clear later on. I rather preferred to feed my curiosity for other culture and traveling around the world and working in different countries. Okay, now what is planetary protection and how it originate? Now, let's get priority right and let's manage expectation. If you would have asked me the same question back in the days, that would have been perhaps one of my answers. What do these guys do? Are they superheroes? Not at all. I mean, look at my face. I can't be one of those. And we're not aiming to protect Earth from aliens attacks or from asteroids. So this is what we don't do at all. Now, on the serious side, 1967 was an important year for planetary protection because it's when the Article 9 of the Outer Space Treaty was signed by many state parties, which agreed to regulate planetary mission to celestial bodies, including the moon, in order to avoid a harmful contamination. And the same attention was also given to protect our environment, Earth, in case of a mission going to other planets and planning to bring back sample from celestial bodies to Earth. There is a committee called COSPA, an international entity, the Committee of Space Research, who has produced the guidelines to be followed by major stakeholders working in astrobiology missions. However, the message here is that the final accountability and the responsibility, if something goes wrong, it will still be on countries. Now, what are the objectives of planetary protection? Are mainly two. The first one is to prevent the so-called forward contamination. As you can imagine, if you are searching for life, you are using state-of-the-art instruments, then you don't want to contaminate those instruments because otherwise you will have the so-called false positives, which is basically when scientists cannot really determine whether a potential sign of life is indigenous on the planet or has been brought by us. So we have contaminated that instrument. In a way, it's a kind of protect our missions, our investment in space. The second important objective is to prevent the backward contamination. As I said before, there are missions planning to go to other planets and bring back a piece of the planet, a rock, for example. And what we want to do is making sure that there are measures in place in case that sample might contain extraterrestrial organisms. So that Earth environment is not affected by that microorganism. There are already ongoing missions on that, and one of those is Mars Sample Return, which I would like to talk in again in the next slide. Now, you might have seen already this picture already, so I won't dwell much. This slide is only to say that Mars has been the target of many missions in the past, and they will be the target of many in the future. So as such, also planetary protection requirements and regulations, allow me the terminology, are very much Mars-centric. This guy that you can see on the slide is Giovanni Schiaparelli, who is arguably one of the most notable observers of the red planet. And because of his loss in translation from the Italian word canali, which has been translated to canals, he triggered lots of fantasy stories about the red planet, inferring that it was already colonized and there were already civilization over there. One of the most interesting one I found is the War of the Two Worlds, which is one of these fantasy stories. But Schiaparelli wasn't wrong in terms of his observation. You can see on the right picture, taken by NASA, some formation called gullies or channel, we should say, which on Earth are generated by presence of liquid water. We now know that Mars environment was completely different than in the past. Is today very dry and cold. The lack of atmosphere makes it battered by cosmic radiation and UV light, and makes the presence of life, at least on the surface, very unlikely. But in the past, we know there is lots of evidence that there was lots of liquid water, and we generally in astrobiology, if you follow water, you increase a lot your chances to find life. In this context, there is the ExoMars mission. I thought it was good having a little bit of an overview of the mission to put into context the associated planetary protection requirements. So ExoMars mission is the European effort to find life, present or past, on the red planet. And this two-phase mission, the first one has already been accomplished, and it was in 2016 when the Trace Gas Orbiter, which is the picture on the left, was launched. Is now up and running, orbiting Mars, and the main goal of the TGO, the Trace Gas Orbiter, is to find presence of methane. We know that methane, it can be a potential biosignature, which means that it's a gas that can be produced by biological sources, which is why important to understand the origin and why it's there. On the right picture, you can see our beloved, I must say, Rosalind Franklin rover. I've been working in this project for almost 9 years. And this is a rover that we aim to launch in 2022, hopefully land 2023, and to find life potential on the planet. Okay, this slide is just to remind us where methane is coming from on Earth. It's definitely from biological sources like cows. But we know that methane can also come from abiotic sources. On Mars, there is a possibility of a phenomenon called serpentinization, which can generate methane in the presence of olivine-rich rocks and CO2 and water. So it's not a given that methane is coming from biological sources, which is why what we want to find out with the Trace Gas Orbit. What are the objectives of the ExoMars mission, specifically on the rover? So we have a different set of objectives. There are technological ones, because we want to prove our European capability to land hardware and payloads on Mars. But we wanna also make sure that we prove our mobility system, our capacity to handle and process the sample. From the scientific side, we want to help astrobiologists to answer the big question: are we alone in the universe? And so we aim to search for trace of present or past life, but also to characterize the environment and the surface prior to future human mission. Yeah, this is a hot topic for planetary protection, because the human mission and how they will be carried out will be one of the big discussion and the trade-off that we will have to make together with all the major stakeholders. On the left side of this slide, you can see some sketches of the rover. From a planetary protection perspective, one of the interesting equipments are certainly the wheels, because they will be in contact, intimate contact with Martian soil. So you can imagine the level of cleanliness and sterilization should be up to a certain level. And then you can also see here the drill box, which is the house of a 2-meter drill that will be used to drill down and find water ice. Again, where you have presence of water, you increase your chances to find microorganisms and formal life on your sample. On the bottom left, you can see the rover in installed configuration that will be used during the launch, because of it will withstand better the vibration during launch. And on the bottom right, there is a section showing the inside of the rover with all the electronic equipments. And this is where also our search for life instruments will be located. Now, what are our search for life instruments? The main one, the core, is called the Analytical Lab draw. And the picture on the right is the moment where we have installed the Analytical Lab draw inside the rover body in our Airbus Stevenage biologically controlled room. I must admit that day was a quite stressful one for me, because obviously we didn't want to cross-contaminate the instrument with our microbes. One of the main items I should highlight inside that the instrument is called the MoMA, which is the Mass Organic Molecular Analyzer, which is an instrument, basically it's a gas chromatography mass spectrometer, which is able to identify organics and also whether those organics are really indigenous or are coming from cross-contamination events that because we have brought inside the instrument itself. Okay, this picture and table summarize what are the typical planetary protection requirements. Now, forget about the numbers. The main message here is that we have different requirements depending on different area of the rover. If you think about the previous slide I was showing, the Analytical Lab draw and the drill, these are part of the so-called Ultraclean Zone, which is anything in contact with the sample, acquisition, handling and analysis. Anything in contact with the sample has to be really, really clean. I would say almost sterility and very low total organic carbon. All the rest of the rover can be let me say, have a more relaxed requirements. We are talking about the order of 10,000 spores, right? What is a spore? A spore is a specific state of a bacteria which is dormant. It makes it more resistant to the external environment. If microbiologists would allow me the terminology and the analogy, the spores are in a state where they're sleeping, right? And they're waiting for more favorable condition externally to then germinate and reproduce and replicate and potentially create problem for our hardware, which is why we target the most resistant species. But what does this mean? Right, I like the example of a pinhead because it gives you an idea of the level of challenge we face when building flight hardware. Nobody can argue that the pinhead has a very small surface area, but if you are able to have a close-up image of a pinhead or a higher magnification, you will see that the thousands of spores we were talking before to be our requirement can be easily contained in a pinhead, right? Leaving also lots of more available room. Now, think about the 150 square meter of accountable surfaces that we have on top on our ExoMars rover. So the order of magnitude is so different than in those 150 square meter, we can definitely carry lots of more than 10,000 bacteria spores. Another example I would like to make is, humans, right? We are the main source of contamination, right? Has been estimated that every 24 hours, we shed 5 billion of skin flakes. And a percentage of these skin flakes will carry bacteria spores. Now, compare again the 10,000 spore that we have seen before with the 5 billions. There is a big difference. And also compare the timeline. We shed 5 billions in 24 hours. Now, think about how long would it last, the integration, the assembly, the testing, and the launch phase of a mission like ExoMars going to Mars. It takes a few years. So you can see that the challenge is not only meeting the requirement, but also maintaining those requirements over time. This is not news really for microbiology, because we live in a world of bacteria, right? Bacteria are very good for us, for humans. Not all are bad, right? So we always think that bacteria are bad, but they are part of our well-being. And it is estimated that we have 2 kilograms of bacteria in our gut, and we have thousands and thousands of different species. And we just don't want them to be in our fly hardware. That's it. I have nothing against bacteria overall. You might laugh at this picture, but this gives you an idea of wrong, obviously, behavior inside a clean room while building a spacecraft or a lander. There are too many examples of contamination events caused by people. Again, the message has to be that humans, people are the main source of contamination. And this is confirmed by this graph that I put on the right side of the slide, where the red area is contamination coming from people. The rest is from environment and equipment. So we need to target people in a positive way, obviously, in different aspects. I don't want to ruin your lunch, but this is a slide I always add as part of my training to personnel working in biological control area. This is to tell that people have to dress correctly, because a particle, like can be a hair, it can be a problem also for biological contamination. If you look at your hair follicles, even if you don't have dandruff, it will be full of colonies. And then in the center, I put a picture of an agar plate where basically a hair has been put in the middle, and you can see lots of white spot. One of these white spots is called the colony forming unit, and when you start seeing it, you have already millions of bacteria in there. So what do we do then with people? Right, there is only one recipe really. You need to have training, awareness, communication, and dialogue. Use lots of soft skill, explaining the people why we need to dressed in a certain way while working on fly hardware, explaining the behavior, the acceptable, the unacceptable, the attitude that you should have, the do's and the don'ts. It's very simple. Less people means less contamination on the hardware. So sometimes in a critical operation for cleanliness, we have to limit the number of people working at the same time. But it's really working together. In this case, it's not like a slogan, something that we say because we have to say we work together. But if you think about the number of people that work and eventually are in contact with fly hardware in a project going to Mars, these are hundreds and hundreds, and coming from different backgrounds, from procurement, from project manager, from mechanical and electrical engineering, from technicians, from the cleaners. I mean, you might think the cleaning is an easy operation, straightforward, but it is not the case. If you're not careful, if you not use the right chemicals and the right protocols, it can become a serious problem for the hardware and for your clean room. You can create contamination events. So all these people has to be trained accordingly. I have had two of my favorite pictures during the assembly operation of Rosalind Franklin rover. The top one is showing the mechanical team putting the lifting device on top of our rover for the subsequent lifting, which is representing the bottom picture. We wanted to basically calibrate the yellow antenna that you see on the back of the rover. This is called the wisdom antenna that will be the radar basically that will spot water ice, and that will tell us there is ice, and then we will start drilling in there and getting the sample. I remember that moment was quite stressful for the people working inside. We had a very tight schedule. We were desperate to go ahead and to go to the testing phase and get things done and go to the next phase. But still, you can see people dressing properly with full bunny suits, with face masks, with overalls and goggles, double sterile gloves. But the message here is, if you don't have the right training and the right refreshing and awareness in this difficult moment, you can make error. How do we measure contamination on spacecraft? Airborne contamination is measured by witness plates. So the top left is an example of a molecular witness plates. When I say molecular, I should really say organic, which is the contamination coming from all the polymer adhesive pollutants, which are used in huge quantity when we build flight hardware. The best example to say what organic contamination is if you think about a new car, you get on a new car and you start smelling the off-gassing product, the volatile organic compound that they come out. This is something that you cannot see, but you can smell. And then that is potentially a problem for optics, for instruments that we have on board. Because it can deposit on the surface and create problem, or it can basically leach in our search for life instrument and create false positive. So we gotta be able to assess and count that type of contamination. And you can see a yellow zinc selenide window where contaminants are collected and then extracted with Fourier transformation, infrared analysis, and check the family. Or on the top right, you can see a particle fallout plate which collect particle by gravity, and then those particles are counted and assessed against the requirements. The bottom left is on the biological side. This time is an air sampler, which is able to suck up to 1,000 liters of air. The air is pushed through a plate, which will collect any contaminant on the air, and then the agar plate will then be incubated and colony developed and counted. Or the bottom right is an example of an agar plate which is usually put between 2 to 4 hours, exposed close to the flight hardware or critical operation, and then colony forming unit counted afterwards. In terms of contamination on surface, biological contamination, there is an ESA Space Agency approved methodology, which is quite straightforward. It consists of a sterile swab or a wipe, depending on how big is the surface. And you swab the surface, you put in a sterile water vial, and then you perform the so-called heat shock, which is about raising the temperature to 80 degrees and then cooling down to 10 in order to kill the less resistant microorganisms. We want to only remain with the so-called spores. And then this solution is then spread through different plates and then incubated at 32 degrees. And then after 72 hours, you count the single colony, and you have, with a mathematical formula, the final number of bacteria spores. Now, what I'm currently investigating with the astrobiology team at the Open University is alternative methodology, or I should say complementary methodology, to have an understanding also of different bacteria. Because if you think about this methodology, it only identifies a specific type of bacteria, which is resistant to heat shock, is aerobically, is respiring aerobically, and is an endospore. So basically, we want to be able, especially for future mission, to identify different species and to tailor our planetary protection measures against our funding to take informed decision. Also, if you think about waiting 72 hours before getting the result, that for industry is a bit of a problem because obviously the schedule is more and more tight, and we want to have a more rapid results. We use different serialization methods depending on the hardware. The most common one is the dry heat microbial reduction, which basically means raising the temperature higher than 110 degrees, dwelling for a certain duration, and under certain humidity condition. Or we use gamma radiation. We bombard the item with gamma ray, very effective method of serialization. Or we use hydrogen peroxide for surfaces. Or isopropyl alcohol, generally in a percentage of 60 to 70%. Any of this methodology has their own pros and cons. If you think about, for example, a lubricant, a grease, and you raise the temperature, the problem can be to separate the solid from the oil phase and have problem or lubrication, or even contaminating with oil. Or if you have an adhesive of a polymer, which is used for structural bonding, if you raise the temperature, might create a problem you can decrease the strength of that bond. Somebody might say metallic material can be okay for high temperature, but we have experience in the past where, especially if you have a very fancy geometry, very thin layer of metals and different metal put together, like aluminum, stainless steel, and titanium with complex geometry, and you raise the temperature, you can create deformation. So you need to be careful. Or if you use hydrogen peroxide, you can oxidate the surface. Electronic material are another type of problem, because even without being an expert, the solder joints are made by thin lead. They can suffer a very high temperature, or hydrogen peroxide might affect the solderability and the coating that we use on top of printed circuit board. So the message here is you need really to be careful and tailor your serialization process, comparing it with your hardware. Some picture of our clean room in Stevenage at Airbus. I must say it's a state-of-the-art clean room, but again, the message here is that the BioClean facility is not a magic wand. If you start behaving in a crazy way inside, if you start running or sneezing on top of your hardware, then it does not matter if you have a very good clean room. So it's essential, it's really important, the attitude of people inside. But obviously, it plays a key role, having such a good clean facility. Only few walls you can see mainly is made of stainless steel. The walls are stainless steel, and the reason of that is because we want them to be very cleanable, and also to limit the organic material. The main contributor for organics is the floor, which is made of a resin with anti-proliferation of bacteria technology. There is a positive pressure inside. The air is pushed from the top, from the ceiling to the bottom, and there are lots of changes of air to help contamination inside. One of the features, this is the right image, is what we call the air shower. So it's basically 45 seconds of treatment with a very high pressure, clean and filter air, which aims to get rid of all your particles that you would accumulate during the dressing procedure. And the bottom picture is only one of the activity during the assembly in Stevenage. Some other picture, only to give you an understanding and the size of the facility we have to deal, which is not an easy task in terms of contamination. If you see, for example, the middle picture, this is the thermal vacuum chamber that we have used during the testing for our rover. And you see the size is more than 10 meters high. The rover is in the middle. You might see it in the middle of an infrared grid. And the thermal vacuum test is done for simulating the thermal and vacuum conditions that the rover will experience during mission. But you can see how difficult it is commission from a biological perspective all these big areas. Or the right picture, this is representing our EMC, the electromagnetic compatibility testing inside our anechoic chamber. The wall is made of very nasty, from a contamination perspective, cones, which are very porous, are made of a resin which can absorb contamination and leach out with time. So you need really to be careful, and you have to have a real step-to-step understanding and perform a proper military exercise, really, because any step can be a problem for contamination. Okay, the Decommission I would like to give you an overview is the Mars sample return. As we said, the mission aims to bring back sample from Mars to Earth. There are many reasons why scientists want to do that. One is that there is a limit on size and weight for an instrument that can be carried on board flight hardware. Or, for example, we want to have a fundamental aspect from a scientific perspective, which is the peer review. We want to be able to, communicate and having a double opinion or triple, I would say, analysis in different labs. Okay, that obviously you can do on Earth, but you can do on the red planet, obviously. So the Mars sample return mission is a 3-phase project. The first one is already been accomplished by our colleague at NASA, and there is a rover already, Perseverance, up and running, which will be soon making science and collecting samples and put inside tubes. 2026 will be the launch of a second mission, which will carry the so-called sample fetch rover. We'll go up, collect those tubes and go back to the platform, and then there will be an ascent vehicle going up, orbiting around Mars, and in the same years there will be a third mission carrying Earth return orbiter that will rendezvous the sample, catch it, go back to Earth, release the container, and then deviate trajectory, and the samples will then be analyzed in a dedicated clean room on Earth. What could possibly go wrong here? So just to give you a little bit more picture of the mission. So Perseverance is already up and running over there on Mars. Sample fetch rover will be collecting the tubes, go back to the lander. Then will be the so-called MAV, which is the Mars Ascent Vehicle, which will eventually release the container with the sample. The rendezvous with the Earth return orbiter will catch the sample, well, I should say the container, and then on its way back to Earth, will release the container to be analyzed. Airbus Defence Space is prime for the sample fetch rover, which is the one on the left, and for the Earth return orbiter. Especially the sample fetch rover will be built and tested by Airbus Stevenage. You can see it's a very much smaller rover, much more quicker than the ExoMars one. Maybe you can see the canister, which will house, I think, 36 tubes, which will weigh between 3 and 4 kilograms. And then the wheels are very much different than the one we use on the rover, the ExoMars rover, because I'm much more flexible. And you can see the cameras on the top of the mast and the solar array. Now on the right picture, there is the Earth return orbiter. This mission is led by Airbus Toulouse from an industry perspective. And then, as I said, we'll catch the container and go back. Now, from a planetary protection perspective, now what does it mean, this mission? Right. So first of all, we have a category 5. In planetary protection, we have 5 types of category, 1 being the less restrictive and 5 being the more restrictive. Now, it's also restrict Earth return, which means we need to take measures because of potential risk of the samples containing extraterrestrial microbes. Now, this risk has already been assessed by agencies and the international community and even independent boards. And I must say that the risk of a sample containing an extraterrestrial microbe is remote, which is also negligible, the risk that even though there is a potential microorganism, the microorganism can survive on Earth. But still, because of the importance of the topic, we are still treating the mission as the microorganisms could really affect the integrity of our environment. And how do we do that? Right. First of all, there are different bullet points I would like to talk through. The first one is the canister holding the samples returned from Mars shall be hermetically closed with a qualified process and agreed by all the stakeholders. The main goal is to break the chain of contact, which means any material which is in contact with Mars, it shall be either sterilized with an approved methodology or hermetically sealed. And then there will be different stages, different steps of reviews and approval, where we will assess the situation prior to launch from Earth, prior to leaving Mars, to return to Earth, and prior to agree and commit on the Earth re-entry of the container. If one or is during one of those milestones something goes wrong and will be detected, then will be the potential to stop the mission. Also there will be lots of what we call the PRAs, which is probabilistic risk assessment analysis, because we want to really decrease up to, I think, 10⁻⁶ probability that we release a size of 50 nanometer of particle on Earth atmosphere, because it's not only the Earth surface that we want to protect, but also the atmosphere. There will also be, obviously, probabilistic assessment from the forward contamination perspective, because we want to also protect Mars, because we want to make sure that the orbiter around Mars won't be crashing and contaminate the planet. Now, concluding, I think planetary protection is something that is a discipline that contains lots of sub categories. In that respect, I think is a little bit like astrobiology in general. It's something that you don't learn at school, really. There are different areas where you specialize, and then depending on what you do, you contribute to the community. And planetary protection can be divided in the same way in different categories. So planetary science is one of those. You need to know about the planet you are going and the environment to target your requirement and to make sure that everything will be okay. There is an ethical landscape. I didn't talk so far about ethical aspect because it's not an official, let me say, objective of planetary protection. However, there are ongoing discussion on ethical landscape. Question like, even if we find life, are we entitled as humans to interfere with it? They are getting in the loop and in the planetary protection discipline. Contamination control is one critical aspect. So how to minimize contamination within particle, organics, or biological, are all part of the same type of contamination. All of those shall be contained. There is a lot about material and processes, material compatibility. You've seen all the serialization processes, the way they can affect hardware integrity has to be tested and demonstrated. And then you have lots of mission planning. If you don't involve planetary protection from the beginning, it is a problem, basically, because you might find issue later on down the line that will potentially have a much higher cost for the project. And there is COSPAR, the Committee of Space Research, so international policy that are not cast on on stones. I mean, this policy will change depending on the discovery that we will make from an astrobiology perspective. Discovery of water on different planets will result in a change of those policies. And obviously you need to know about microbiology, especially this is a field where I think we should invest in the future for astrobiology missions, knowing how microbes behave and whether or not they can survive during the journey, during the mission to a specific target body is essential. It will give us knowledge in order to tailor planetary protection regulation and measure. The thing is, the message is, if you don't know about those aspects, about whether or not a microbe can withstand conditions, then what you do, you are more conservative because you don't know. The unknown makes planetary protection measures and regulation to be more restrictive, as we need to take informed decisions. Okay, that is it from my side, and I'm happy to take any question you might have.
Thanks so much, Silvio. That was fantastic. And it really an in-depth look at, even though it was so quick, but an in-depth look at planetary protection and how it works in practice. I think a lot of our audience over the past 4 weeks have been really interested in how planetary protection works on a like a realistic and level. And how we can reduce the impact of our personal microbiomes on other planets. I'm thinking of my own hair microbiome as you were talking, and the fact that my body is shedding billions of skin cells every day. So I think that's really, it puts things into perspective about how big a task it is to do all those things and make sure that we're being safe going out into the world. My first question leads on from that, and it's about manned missions in general and whether they will inevitably fail to be perfect in the regulations due to human error, especially if it's just about humans doing things to reduce the impact themselves. Do you think that the decontamination process or the regulations are rigorous enough to reduce the possibility of human error?
I think this is an area of obviously development, and where the research in the next year, in the next decade, should go really. What I tried to say before during the presentation is that if you don't know, the unknown makes planetary protection regulation and measures much more restrictive. Which is one of the main messages. So I think we should invest on knowing more and more about humans and how microbes can interact with the target body. Now, the most likely thing that will happen is having a human mission on Mars. And in terms of planetary protection, I don't think you would be able to say, okay, we need to carry 10,000 of spores like we have on on ExoMars. But I think what we should be doing is learning from the current mission, ground-based mission, or the International Space Station is another one, or Artemis, or a future mission, and have a real understanding of microbes behave, and but also develop from a technological perspective, develop a methodology for I don't know how to dispose the waste if you go there. A big it's a big topic, but what are the interaction of our microbe with the surface on Mars, and is there a problem or not? And so I think we are still in a stage where we have lots and lots to learn, and also for backward contamination. because if you think about, humans going to Mars and then they need to go back, so all the quarantine measures, what do we do with that? So there are lots of areas, I think, where there will be lots of discussion, and the more we know, the more we interact within the international and scientific community with all the stakeholders, the better will be, the more sustainable we can carry the mission.
Yeah, I'll ask one more question, and then I'll pass over to Lucinda, who's probably got lots. I'm interested in what the development of regulations over time. So the original manned missions to the moon, are they as rigorous as what we'd now have going to the moon, or because is there potential that something went on there?
Right. That's a good question. There have been lots of incidents. Let's call them. I got in mind the tardigrades, event. But I think it was discussed, and I think now, if I'm not wrong, there is an idea, a NASA interim directive that basically is dealing with a little bit more with this aspect. If now, I talked briefly about category on planetary protection. I think now the idea is to basically have a more restricted category for a certain case on the moon. If you think about the PSR, the so-called permanently shadowed region, which are very important for understanding the origin of the chemical and the life of the planet, I think those has been upgraded to a category 2, so there will be a little bit more of measures to be taken. Or I think the other region will be this time both for historical and scientific reasons is the Apollo area, where we have the lander with other biological waste put there. So all these areas which are basically more important from a scientific and technological perspective are being taken into account. Any incident, any error has obviously to be addressed and taken into account, and this is, I think, where we are going, especially because if you think about the moon, it's not only the moon. In planetary protection, we have the system Earth-Moon. We don't want to, for example, for backward contamination, when we bring back samples from other planets, we don't want to contaminate the moon either. It's not only about Earth. Because we wanna retain that free traveling between Earth and the moon, and if you contaminate the moon, then you might need to rethink a bit the aspect.
Thank you for those answers, Lucinda.
Yeah, really interesting talk, Silvio, and definitely lots of unanswered questions. We do have quite a few questions from YouTube, the Royal Astronomical Society channel. I'm going to ask you one, and then I have a second question, Joan. I'm going to try to combine some to keep them all succinct. But Sally from YouTube, she's asking, are there any similar measures on Mars? You're dealing with ExoMars. I don't know how many different other celestial bodies in the solar system you might have to control for, but you're currently focusing on the ExoMars rover going there. But she wonders if there's any sort of pro-landing decontamination. Let me just make sure. Hold on. Could they release? Post-landing decontamination, because she mentions like there's going to be a probe sent to Enceladus that's going to heat up so high that they want to melt the whole instrument. So, and I know we've already sent so many things to Mars. So about Mars, where we don't worry about that too much.
The next the next set of missions are definitely the so-called icy moons, the Jupiter, especially. I mean, Europa is one of the targets. Again, if you follow water, you increase your chances of finding life. But you're right. For example, if you think about the methodology we use now for assessing biological contamination, it won't be enough for those missions. So we don't know much about the environment itself on the icy moon, for example, to say we have a clear idea of what we want to set as a planetary protection requirement, which is why I think from an industry perspective, I decided to have this part-time PhD with the astrobiology team at the Open University, because I think there is a gap between industry and scientists, right? Not that big, but I think we have to basically communicate more and more, and only by working together and understanding the two sides, we can make sure that that the mission will be successful. If you think about our hardware, how we industrialize our instruments. Sometimes it would be really good, for example, to invite the scientific community to the industry side to see the challenge we face practically, because on paper and theoretically it's all good, but also from the practical side, it's also important to understand the requirement, and also from the industry side, I must say we have a lot to learn, because we need to be able to understand the bigger picture. So why we do certain instruments, because only that way then I can go back to my colleagues and to the project and say, this is why we do that. This is why we should be careful in doing, what we do. And I don't know if I deviate from the question, but for talking about icy moons, it would be really interesting to see whether a certain type of microbes that we carry on our flight hardware are able to withstand to the journey condition, to the radiation, very high radiation environment that you will have there, and to the very harsh conditions that you will experience on those habitat. So that is definitely something that again the research should go, and we should investigate to tailor planetary protection measure and to take informed decisions.
Yeah, I was so impressed by all the different disciplines that it takes to do the job that you do. And obviously you can't know everything. So absolutely communication among them, super important. I guess can ultimately, what's the difference about Mars? Like, so we had Spirit and Opportunity there. We have Viking still there. There's nothing, I guess, that they've done now that their missions are over to worry about leaving them on the planet. Same with the moon, I suppose. But do you think there's any specific reason why that they're not doing anything for that?
I don't know really. That's a good question.
I think I heard like the radiation levels on the surface of Mars would pretty much decontaminate things naturally.
That's right. Yeah, that's right. On the surface, the problem is really is not really on the surface, because again it's battered by UV and cosmic radiation and so on. Also, there is a very oxidative environment. You have perchlorate salt, which does make the presence of life unlikely. The problem is when you contaminate the water on a planet, and back to the icy moons, if you contaminate the water, then you will have a systemic contamination. One single microbe that can withstand those conditions and resist and replicate, then it might be a big problem for both, let's call it ethical aspect, because we contaminate another planet, but from a scientific and technological perspective, because we won't be able perhaps to find whether the life was indigenous or we brought there.
Joe, I have another question. I don't know if you want. Okay, go ahead. Thank you. So, I mean, a lot of these questions, I'm going to surmise them a bit. So someone talking about, algae found outside the surface of the ISS recently. They discovered something growing outside the ISS. We're going to have private companies who want to do, like you mentioned, Bereshit that just landed something on the moon. I think also there's been a private company who's been allowed access to the moon to also do a probe on the moon. And of course, to Mars. So what about planetary protection to those private companies?
Yeah, this is a priority. You are absolutely correct. We have to start as sooner rather than later, a dialogue with private company. Private company, we need to think about, I mean, they have a very big chunk of investment on the space field. So it's, you know, we have to start talking, because they might not have necessarily the appreciation of what a planetary protection requirement, why we do certain things. And again, as always happens in the scientific community, I think that has to be tackled internationally. With all the stakeholders involved, the microbiologists, the planetary protection, the chemists, the geologists, and you know, we need to start talking with them, because they have the right, because they are investing on space missions, and then we need to consider that as a fact, and start talking with them also about this aspect. It's definitely a priority.
Yeah, just like ExoMars is working with ESA, you know, SpaceX is working with NASA, another, you know, space agency. But I'm going to hand it back over to Joe.
Yeah, it's also interesting. I think we could talk for a long time, and we've actually got lots of questions still in there. But I want to switch gears a little bit and talk about your career, because I think that's something that's really interesting. And what strikes me is the internationality of it, and how you're based in Italy, but you went to Alicante, and then you've ended up in the UK. And I was just wondering if you could talk about that experience and what it's like to work so internationally. And maybe talk about Erasmus.
Yeah, right. I think I'm, my attitude as an individual is I'm very curious, right? So I want, I like, using my soft skill and knowing a different culture and stuff. And I think, I think I do recommend to anybody to go out and have a look at other countries and other cultures are, because again, if it's similarly to the technical aspect. If you don't know, you basically have a negative approach to things, right? It's only the unknown that makes you fearing, let me say. If you start understanding and talking to people and where they're coming from, and you realize that it might be part of their culture, and it's not necessarily because they want to be bad with you. And I think in the work that helps me a lot in the work I do, because I'm interfacing with customer. I'm basically in the middle of internal customer, external customer like agencies, NASA and ESA, European Space Agency. But I'm also dialoguing with subcontractor, all the supplier making the equipment. So understanding where they're coming from, what's their point of view, all the aspect. I think the experience I gained over the years of going in different countries and meeting lots of different culture. Helped me a lot, because, for example, I know that I cannot make everybody happy. That for sure, because I'm stuck in the middle. And but I think people will respect you if they know and understand where you're coming from. That's why dialogue is really essential for the work I do. And definitely, I do recommend anyone to go outside and spend abroad a period of time to have a look what is looking like living in another country.
Yeah, in terms of like your day-to-day job and who you interact with, are you interacting with lots of people from all over Europe and beyond, or do you find yourself in a small bubble? What's it like?
No, I think I'm lucky enough to be involved in international projects. So I used at least to travel a lot for work, in the US, in Canada, but in Europe, where all the provider of the equipments are. And if you think on the rover, on the ExoMars rover, we have more than 20 equipments coming from all around the world. And every equipment is a challenge, not only for the technical aspect, because obviously also culturally they might be lost in translation, like Schiaparelli had with the word canali. So basically, it's I found myself. I think I'm really lucky in that respect, because I can interact with different people from different backgrounds and different culture and nationalities.
Fantastic. It sounds like a fantastic career to be in, and an environment to be in as well. To work.
It's stressful at times, but I think that's normal.
Yeah. So thank you very much for your time today and for your talk,
No
and
worries.
for answering as many questions as we could get through. I will wrap up now, so that we don't stretch on too long. But yeah, I just wanted to say thank you very much from both myself and Lucinda at the Royal Astronomical Society and the Linnean Society as well.
Okay, thanks for having me. Thank you.
Thank you, Silvio. It's fantastic. I guess we want to also mention how exciting, going on from planetary protection to space materials. We're going to be having some new speakers in June. Thank you, Silvio, for being with us and continuing on this incredible conversation about astrobiology and all the multidisciplinary connections to it within science. And wow, it was just, that was a big graph that had a lot of different disciplines in it. But thank you so much. We are going to take a break next week. Is that right, Joe?
That's right.
Because it's half term.
It is half term, and then we'll be back with 3 more in June, where we're looking at astrovirology, viruses in space. We're looking at space materials, and we're looking at analog research. So check that out on our websites, and we'll be back soon.
Yep. Bye, everyone.
Thank you.